About what? Thesis, yeah, I got the thesis, yeah. No, that's fine, yeah, that's good. Okay, that's the kind of a project selection summary that I have. People have emailed me. I appreciate a very quick response from almost all of you, and just a confirmation that I got the right information from you. Are there any questions on the project? So get started on the literature part, and if you want to talk to me, please drop by. There's one person that hasn't picked, but I guess he's not here yet. So, any questions? Okay, so in the last class we kind of reviewed basics of linear algebra, went through the concept of definition of a determinant, the LU representation, inverse of a lower triangular matrix, and Gaussian elimination, Thomas algorithm being a variant of that. And towards the end I concluded saying that the Gaussian elimination is one of the most efficient direct solvers for solving large system of linear algebraic equations. And the only one that's probably more efficient than that is still Gaussian elimination concept, but knowing the fact that certain elements in the matrix are zero. And these are called sparse algorithms for sparse matrices. And I think you got a chance to use them in MATLAB exercise in the first assignment to see how efficient it is, and particularly as you increase the size of the matrix to 1,000, 10,000, 100,000, etc. Now, the sparse matrix algorithms are very, very sophisticated. I don't even understand, I pretend to understand that, but I use it. I've used it in my research very effectively. Basically, the ideas that go into sparse solvers are, as I said, elimination, but if some element is zero already, you don't need to eliminate that, right? So you recognize that. So you do a pre-analysis of your structure of the matrix, knowing which, so the way that you input the data into the program is not the entire element for Aij, but give a triplet values. What is the row index I? What is the column index j? What is the value? Okay. Typically only 10% of the matrix, that's by million, but only 10% of it may be non-zero. So instead of storing lots of zeros, you store only the non-zero elements. So you give it I, j, and s. That you would have seen in the MATLAB assignment that I gave you, how to input a sparse matrix or how to extract that information. If you give it a general matrix, MATLAB has tools to do this analysis and extract this triplet of I, j, and the coefficient value itself. And then it uses sophisticated graph theory analysis to say, if these are non-zero, as I eliminate, which ones that were zero originally can become non-zero, because I need to allocate space for them as well. So very sophisticated algorithms using graph theory figure that out once and for all. Once they know the structure, then they do the LU decomposition on the sparse matrix, but store them also in the most efficient way. And these are just like LinPack, LabPack, ScalaPack. There is something called SparsePack that's available from Waterloo, I think. And MATLAB essentially assimilates all these things. So the MATLAB implementation of sparse algorithms comes from SparsePack. But SparsePack itself was written in Fortran, and I think it still is available for download. So that becomes important when you're dealing with really large, very large system of equations. Today what we are going to do is continue this journey of surveying various ideas in linear algebra and look at the contrast between direct methods and iterative methods, and why iterative methods are much more powerful in solving very large systems. So towards the end of the last lecture, we talked about this Gaussian elimination and LU decomposition, the relationship. So the symbolic representation of a Gaussian elimination can be done like this. Okay, so here you see that given a matrix A that is full, dense, meaning there are no non-zero terms, it is these operations that you see in the first column with a matrix that has ones everywhere. If you carry out that vector matrix multiplication, and this is a lower triangular matrix, but it's not only a lower triangular matrix, it's a very particular structure. The first column is non-zero and the diagonals are non-zero. Everything else is zero. Okay? And it can still be represented as L1. That is the first step in the elimination process, is captured by these operations. So if we carry out the row and column multiplication and set it out equal to the right hand side, you will see that is the operation that makes these elements zero. Essentially what we are doing in that elimination step is getting rid of x1 from all the equations 2 to n. Okay? From the second equation on to the nth equation, getting rid of x1, eliminating x1 from that by this operation. This is exactly the operation we saw in the last class, and we wrote a MATLAB code around a loop, a for loop for that. Okay? But once you get this matrix, this is still, it has some zeros, but it's still full. Okay? And this is A. Okay? And we are taking the right-hand side towards a U matrix, upper triangular matrix. Okay? And you continue, so this is symbolically represented by L1 times A is equal to U1. It's called U1, but it's really not an upper triangular matrix. Just one variable has been eliminated. And you take U1 and multiply it by another matrix, and this is not how you would actually implement the algorithm. The steps are exactly the same, but if you have a matrix multiplication like this, it turns out to have more number of multiplications and divisions than the algorithm that we saw yesterday. So you take a second matrix L2 that is also strictly lower triangular, but it has a non-zero element in the second column. And these operations also were figured out yesterday. That will eliminate x2 from the third equation down all the way. Okay? That is, it will make the second column elements below that into 0 and the diagonal element into 1. Okay? So that is defined as L2. Now L2 is defined in the sense every element in here is known. So we can actually assemble this matrix, carry out this vector matrix multiplication, you will get this. Just like L1 was also defined in terms of known coefficients in A. So what you see is a sequence like this. So the LU decomposition is nothing but a sequence of matrix multiplication starting with A to produce a sequence of matrices that eventually lead to a strictly upper triangular matrix. And it is a product of a whole set of lower triangular matrix, each one representing elimination of one variable. This matrix multiplication eliminates x1, the next one eliminates x2, etc., going all the way to n minus 1. That eliminates the n minus 1 variable, and we have in the last equation only n as the element. The product of all this is also going to be lower triangular. Okay? So Gaussian elimination in concept is nothing but taking the matrix A and splitting it into two matrices L and U. Okay? That can be done in an abstract sense, as we saw earlier, and that's the most efficient algorithm. Gaussian elimination itself is the most efficient algorithm. But in Gaussian elimination, what we saw was you must know what the right-hand side is also before you can apply those operations to get the solution X. In LU decomposition, we don't need that. Okay, so B can be given in a different number of values for different solutions, but the decomposition of A can be done into L and U through this. So Gaussian elimination is nothing but LU decomposition, but done in the abstract without the knowledge of the right-hand side vector B. Okay, so that gives you L times A is equal to U, or A is equal to L inverse U, but L inverse is also lower triangular. Okay, so that is same as L bar. I'm just going to say L bar. So A can be split into this. We saw this yesterday in the last class by saying that when you do this, you treat both L and U as unknowns, and you have two n square unknowns, n square in each matrix. And you have only n square equation, because every element in A must be equal to the product of L and U. And we saw that you can exercise this excess degree of freedom of n square by making one lower triangular and the other one upper triangular. Okay, any questions on that? So the essence of idea that you need to hold from this is Gaussian elimination is nothing but LU decomposition. But it can be, LU decomposition can be done without the knowledge. This is not the best algorithm. It's an algorithm that shows the connection between LU decomposition and Gaussian elimination. But the most efficient method is actually given here, okay, in the next section, okay, where you have recognized that there are n square degrees of freedom, and you use those degrees of freedom to make the upper part of L 0 and the lower part of U as 0. But you are still left with n degrees of freedom, okay? And you can choose that to be specified as every diagonal element of U is 1. Now, when you do that, you will have essentially exactly n squared unknowns and n squared equations. N squared unknowns coming from on the lower side and on the upper side. And once you carry out this product, it's equal to the right hand side. So there will be n squared equation. That is the we are going to develop an algorithm based on this idea that I have a matrix L and a matrix U. When I multiply it, I want to make it equal to the given matrix A. And once I have done the decomposition, I can store it forever, and you give me a different right-hand side, I can just, through a matrix vector product, I can construct the solution very efficiently. So this is all about doing the calculation in the most efficient manner, preparing ourselves for large systems of equations. Now, the idea here is really nothing new, because we have already seen how to invert a lower triangular matrix. We just need to sequence the equation in such a way that you start from the bottom and go up, so that every time of the n square equation, you have only one unknown in that equation. If you do it in an arbitrary order, every equation will have many more unknowns. So you will not be able to solve for them in a systematic manner. So what is the order? The order is, for example, take the first row multiplied by the first column, set that equal to A11. And you will find that L11 times 1 equals A11. So that gives you that L11 is equal to A11. L11 is the only unknown. Okay. Next, what do? You take the second row with this. If you take the second row with the second column, what happens? You'll be in trouble, right? Because you'll have L21 times U12 plus L22 equal to 0. There are, all three of them are not known, right? So what should you pick? Second row and first column, right? Second row and first column. Okay, then that will give you L21, and everything else is multiplied by 0. That must equal to A12. L21, sorry. Okay, and that, once you detect a pattern like that, you generalize that and you say for every Li1 it is equal to Ai1. So you put a loop around that. So you found out all these elements by just solving one equation in one unknown kind of a constraint. Okay, and then the rest of them I have followed the same logic. What you need to do after this is go to the row. You find out all U11, U12, U13. Okay? So then come back, find the second, but go from the bottom to the top. Then go to the right hand side, do this. Come to the left hand side, go up like this. If you sequence the calculations like that, you will find every time you will have only one unknown. All the other things appearing in that equation would have been found. So it's very important to sequence the calculations in such a way that you achieve this with a few loops. And I have those 4 rules. Okay, the first starting one, first column, first row of U, and then from the second one, it is all the Lij's, but going from I equal to j to n, and j equals 2 to n. So there are 2 loops around it, but they cannot be done in one. We have to alternate between these 2. So the program has to be written in such a way that you do this, then you come and do this, and then you go back and do this for the next column, go back and do this for the next row, etc. If you alternate like that, you will get both the factors L and U in the least number of operations. Okay. Again, I have attached a MATLAB code, and I would like you to kind of study that. And MATLAB has a built-in code called LU. Okay, and it will return L and U. And MATLAB code is much more sophisticated than what I wrote, because if you get into problems of 0 on the diagonal, it will pivot, and it will then keep track of the exchange of rows. So it will actually return another matrix called P, the permutation matrix. Okay, but in mine doesn't do. So it works. It's again a naive type of a Gaussian elimination type of a thing. So if I have a division that's a very small number, I can get into trouble with this algorithm. Okay, but MATLAB's LU decomposition would automatically switch the rows to keep the numerical accuracy. Remember, the lesson that we need to learn is when you have a division by a small number or subtraction of 2 very large numbers, you introduce what kind of error? That's a final exam question, right? In oral exam. What is an important 2 sources of errors in numerical methods is round-off error and truncation error. So in this, you introduce round-off errors. Okay, so when you divide by a small number that produces a large number, and then you are subtracting one large number from another large number, you can introduce significant round-off errors. And that destroys the solution. There is no way to get rid of that in the algorithm itself. Okay, but iterative methods are not like that. Iterative methods have a natural way of getting rid of any errors at any step. And we're going to see some of them later today. Okay, any questions? Okay, so once you get the LU factor, why is it better than the Gaussian elimination? Even though essentially they have the same count in terms of computational effort and the same ideas in terms of elimination. But as I said earlier, you can do this without knowing B. Do the LU decomposition, and then you give me a value of B. I can construct the solution through matrix inverses. L inverse B, I call this as B prime, and then U inverse B prime, that gives me X. Inverting a triangular matrix is extremely easy also, very efficient, right? So you do the LU decomposition of A into L and U, and then you invert them and save them. Then it's just a matrix multiplication. You do the inversion only once. For linear systems, those things are extremely efficient. Okay. Now for nonlinear systems, these matrices would have to be updated with every iteration, and that we will see later. So this is the reason why you can, as you come up with different B, I can construct a solution very easily because I already know what L inverse is and what U inverse is. Where does this occur? In solid mechanics, it occurs in B would be a forcing function, a load on a structure, for example. As you change the load, how does the stress distribution work? In fluid mechanics, it is essentially inlet flow rates, velocities, boundary conditions that determine the B term, the forcing term on the system. Any questions on direct methods? Okay. How many of you know about iterative methods? What are iterative methods, and what do you know about iterative methods? What kind of iterative methods do you know?
I don't know. you give them a margin and they calculate it back and forth to get the right answer. So if there is a loop and it calculates the result and the error, and you will give the loop the acceptable margin for error, and when it reaches to that amount of error, it gives you the answer.
Exactly.
Like central difference
Central differencing are approximations for derivatives, and we are going to see that as a method of solving differential equations. But once you have a central difference method, you reduce it into an algebraic equation, but the algebraic equations can be solved in an iterative manner. Can be solved in a direct manner, but for that you need to assemble the matrix, and you can also solve it in an iterative manner, and that captures essentially what the idea behind an iterative method is. So essentially it is something like this. You have ax equal to b is the given problem to solve. So you're given a, you're given b, and you need to find x. Okay? So the direct method says, I know without making any guess about x, I can calculate every value of x, x1, x2, x3, the components in that, by a sequence of calculations, the algorithms that's given by Gaussian elimination. In iterative methods, what you do is, I'm not going to use Gaussian type of argument. I'm going to make a guess for x, every element in x, x1 to xn. Since I'm making this guess arbitrarily, when I plug it back and take the multiplication 8 times x, it's not going to be equal to b. So I'm going to define a residual vector r, which is going to be ax minus b. Okay, that's not going to be 0. Then I need to come up with a clever way of making the next guess. The next guess can also not be arbitrary. If I'm making arbitrary guess, I will be making arbitrary guess forever. I never get to the solution. What does it mean to go to the solution? Some norm of r should go to 0. That means I need to find that value of x that drives that residual to 0. This concept is very important because this is the basis for the method of weighted residuals, the finite element method. All these ideas come from this notion that if you give me a problem, I can construct a residual, an error, and I can construct a solution, and by searching on the solution space, I can minimize the residual. Okay, finite element method works on the same idea as we will see later on. But that's it. So you need to come up with a guess. You need to come up with a scheme to update your guess that will drive you towards correct solution. Now the beauty about this method is it will drive any errors to 0. So even if you are introducing round-off errors during your calculation, they are just treated as errors in the guess that you make. It's no different than the arbitrary guess that you make. So the scheme would drive it such that it will be the residual will be driven to 0. And so there are combinations of direct methods and iterative methods that have been used. The idea is I would use the direct method because I can get the solution, however corrupt it may be due to round-off errors, through a finite number of steps, finite number of calculations. That will be my initial guess for an iterative method, because the iterative method then would get it down to 0 without any round-off error problem. What is the disadvantage of the iterative method? If you ask me how many times do I have to guess, that has to relate it to the convergence rate. What is the convergence rate of this algorithm? There is no a priori answer to that. Okay? That depends on how bad your guess is. If your guess is very, very bad, you may take a very long time to reach that converged state. Okay, so that's the essence of what an iterative method is and how it differs from a direct method. But let's see some of the ideas and algorithms for this. So given an equation like ax equal to b, we're saying we will reconstruct. Do you have a question? Or?
I have a question. So in iterative method, the convergence of your loop, it only depends on your initial guesses?
No. It depends on the clever idea that you come up with to update your guess. What kind of ideas that you have to come up with the next guess based on the previous guess. And we will see through a few examples that will become clear. Right? So there are different strategies for calculating a new value of x, knowing the old value of x and the residual in some cases. The other cases, just old value of x. Okay, any other questions? So it is that step that is crucial, not the initial guess. Initial guess will determine how many iterations you need will be determined by initial guess. But how fast does it go to 0 is determined by the update scheme, what kind of update scheme that you come up with. So given an equation like this, ax equal to b, the first step is rearrange it in a form that x is not to the power, it is the step number. Right? T equals 0, 1, 2, these are called iteration numbers. You may have all seen this in ComSolve because ComSolve uses iterative methods for solving. Right? So x at the p plus 1 step is some function of x at the p step. That's going to be our initial guess when p is equal to 0. So if you give me this, through some function g, I will be able to calculate x1. Then put it back in here x1 and calculate x2. Put it back in here and calculate x3. Iterate that. How many times? We don't know until the convergence is back, until residual is, the r vector is below a certain value. So r is ax minus b, the norm of that vector. Okay. So the next question is, okay, what is g? How do I define that g? And there are many, many variations in coming up with g, and that is the essence of your iterative method, how clever you are in coming up with an update scheme. So let's look at that this is called fixed point iteration. Let's try to understand the idea of a fixed point iteration for a single nonlinear algebraic equation. The same idea applies whether it is linear or nonlinear system. That's another beauty about these iterative methods. They handle nonlinearity in the same way as they handle linearity. Whereas Gaussian elimination cannot be applied for nonlinear systems, right? But these methods can be easily applied to both linear and nonlinear systems. So let's just take some function f of x equal to 0. That means I need to find what the value of x is such that the function is equal to 0. What is that problem? Graphically, that problem is something like this, f of x. This is the function f of x. And I'm asking what are the values of x at which that function is equal to 0. So I can give an initial guess something like this, and the function is not 0, and I need to find a way of coming up with better and better guesses so that that function is 0. So we formulate the problem the same way as we did for the linear systems, x equal to g of x. G of x is a new function. And we just cycle this back and repeat that until we get convergence. Any questions so far? So here are some specific examples. So here is an equation, f of x equals x squared minus x minus 6 equal to 0. It's a quadratic. You know how to solve it using the quadratic formula, right? There are two roots for this. But we want to learn how that fixed point iteration works so that we can generalize it to higher dimensional system. So the first point that we need to do is, if you give me this, how do I put this in this form? It simply says extract one x from this to the left hand side, move everything else to the right hand side, and call that as your g of x. This one incidentally has two roots, at minus 2 and 3. But here I'm taking this x squared and moving the others to the right hand side, x plus 6, and then taking the square root. So this becomes my g of x. Okay? Now, I can pick x to be anything, minus 5, 10, 100, whatever you want, and put it on the right hand side and calculate a new value of x. Put it here and calculate a new value of x and repeat that. How do I know that I've reached convergence? When the error to this equation is below a certain number, close to 0. But in this sequence, now I have only this sequence. You get the same value, right? I put a value on the right hand side and I get the same value. Okay, that means that they have converged. Okay, that there is no change. That's the update mechanism that allows me to go to that root. Now I have a graphical illustration of this somewhere. This is starting from initial guess of 5 into that put in MATLAB, and you see that it goes to 3. But the convergence is not very fast. You can see that it takes 10 iterations. And Newton method, other methods will converge much faster than this one.
So instead of taking square root of x plus 6, what if we
Good question.
x equals to x squared minus 6?
That's a very good question. You can rearrange it in any way you want. And if you have a problem where it is not possible to rearrange it, you can always add an x to both sides. Okay? Suppose I give you this equation, sine of 10x e to the power minus 2x plus 1 equal to 0. There is no way you can extract an x from that. But what you can do is, you can add x to both sides and treat this as your g of x. Okay? But the method of fixed point iteration is very powerful because it tells us something about when it will converge and how fast it will converge. You can extract all those information by going through this analysis.
And all of them will take the same amount of iterations?
No. Some of them may not even converge. Okay, so there is a condition on G that is needed for convergence.
What about the initial guess?
Initial guess can be anything. Initial guess,
Is going to converge the...
no, there is no guarantee that it will. Any initial guess will converge to a desired root. In this particular case, there are two roots. Okay, so in one case I showed starting with 5, I ended up in 3, but there is minus 2 as another root. So you can ask the question, what initial guess should I make to converge to the other one? And again, there are no unique answers to this, and there are ways of thinking about it that we will talk soon.
The method that we use for convergence, is it the same for all cases or is it different for linear systems?
There are many different methods, and the most powerful method is Newton method, and we will spend some time developing that and extensions of the Newton method, so-called Euler-Newton continuation method for nonlinear systems. And for very large linear systems, the one that you used, the conjugate gradient method, that's a very powerful method. That's very efficient. That works even for linear systems. And that's what is used for very large systems. We will see the ideas of conjugate gradient also, hopefully today. But let's just continue this thought. So this is how I generated those numbers. This is a graphical illustration of what happens to the scheme that I've just indicated. So what we had was x equals g of x. Okay. So I can think of left-hand side, if I plot that, I'm going to get a graph like this, y is equal to x. And if I plot the right-hand side, I'm going to get a graph like this that corresponds to g of x. And when is the solution? The solution is the intersection of these two curves, when the left-hand side equals to right-hand side. So that is my solution. Okay. So you can look at visually what happens to the iteration scheme. If I start with some x0, the first thing I do is put it on g. G of x0, what is that? That's going to be my x1. So g of x0, I just read from this graph, and that's going to be my x1. I take that x1 and put it into g of x. That will give me my x2, right? So that will be this value. So you can see how graphically the progression occurs. Starting from any value, you calculate g of x, set that equal to x, then calculate g of x, set that equal to x. When I say set that equal to x, this is the y equal to x line, right? That's why I go here. And then I come down, and it will converge to that point. As long as the slope of this g is less than 1. Okay, and we will show that analytically later on. I have another scenario that you suggested where I rearrange that equation in a different form. Okay, so these three cases are, I don't know whether I have a label for them. this is 1. The other one would be x is equal to x square minus 6. That's another way of writing it. So g of x would be this function. And the third one would be, oops, what did I do? I think you factor it as x times x minus 1 minus 6 equal to 0, and then write x is equal to 6 divided by x minus 1. So there is no unique way to slice this. You can do it in any way you want, and each one will give you a different g. Okay? And so I've taken 3 such cases and graphically illustrated what happens to the iteration sequence. So do you understand the iteration sequence graphically? What happens here? So for an alternate one, if I start from x0, this is my g. I go to the x equal to 1 line. That's my g. I go to that line. I come here, and I come here like this, alternating between the g and y equal to x. So here you can see that there is a discontinuity. This is the one that is 6 divided by x minus 1. That function that I showed you for g just now, right? Like if you take this function and plot it for g, when x equal to 1, what do you have? G is infinity, right? So you have a discontinuity that is shown here.
So if you pick that as a guess,
So if you pick exactly that as the guess, it's going to blow up because you have division by 0. But if you pick anything to the right hand side, you would think that you will get to this root, but it actually throws you to the other root. This sequence of iteration. Okay. And in the third case, the slope of the g curve is greater than 1. Remember, the slope of this curve is 1. So the slope of this curve is greater than 1. And even if I start very, very close to that root, it will always blow up. It will always diverge. So there is no guarantee that the g of x that you have constructed will always lead to convergence. Do you understand what's happening in those 3 scenarios? The first things to know is in a fixed point iteration, there is no unique way to define g. Depending on g, you can have either convergence or lack of convergence, or you cannot predict which one of the routes that you will go to depending on an initial guess. That's a lesson that we learn from basically experimenting with a model problem. We can do an error analysis of what the error propagation rate is for any fixed point iteration. Okay, so what do we know? This is the given sequence, xi plus 1 equals g of xi. And as we saw, if r is the root, when I put g of r, I'm going to get the same value r. Right? At convergence, when the f of r is equal to 0, g of r will be equal to r. Okay? And so I can subtract r from both sides. So on this side I subtract minus r, this side I subtract minus gr, because they are the same at convergence. Okay, so I start from this equation, okay, and I subtract the same quantity on both sides, and then I divide by xi minus r and multiply. So I'm not changing anything. The reason I'm going through these manipulations is to learn something about when this iterative sequence will converge, when it will not converge. Now I can interpret this difference as what? Xi plus 1 minus r is the difference, is the error. Is the difference between what I guessed at that iteration step and what is the actual solution. So this is the error at the I plus 1 step. That is the error at the ith step. So the error at the ith step is related to the error in the I plus 1 step by this factor. Okay, and what is that factor? You know from something called the mean value theorem, this is the ratio we are talking about. Okay, so if I have a function like this, g, and this is nothing but the slope of a curve between 2 points xi and r. But if the function is continuous, I know that there is a tangent to it with the same slope somewhere between r and xi. I don't know exactly where. Okay, so what this tells me is that it is the slope of G, that is G prime, in the neighborhood of R that's going to determine whether the errors are going to decrease or increase. Are you following so far the logic? So if you go back to this, we saw that this is the slope. So I replace it by the slope, but the slope is at an unknown place psi, okay, in the neighborhood of R, between R and xi. So if that slope is less than 1, then the error is going to be decreasing. So at the near the root, you want the slope of G function, the G prime, to be less than 1. That is the condition for convergence. If you have constructed your G in such a way that its slope near the root is less than 1, you are guaranteed to converge. Is that a useful result to know?
So is it for every point or just one point?
A point near the root.
Between those, right? So every
Yeah.
point should be less than 1, basically. Like, if you know, but it's small, so we don't see.
The problem with that is, you are right.
It's not a linear thing.
Yeah, it's going to be a complicated curve. So you cannot say that G prime is less than 1 everywhere, right? If you find a function where G prime is less than 1 everywhere, then you can say that function will converge. But that's not going to happen all the time. The real problem is you're giving the answer in a form where I don't know where R is. How do I calculate that, right? You're telling me that G prime near the root must be less than 1, but I don't know where the root is. So I have not really helped in saying that either this method is guaranteed to converge or not guaranteed to converge, right? But for certain methods that we choose, you will find that you can actually show that it is guaranteed to converge. It's not only guaranteed to converge, you can say that it will converge quadratically or linearly or somewhere in between. And that's why the fixed point concept has been useful for proving a lot of these convergence results in numerical analysis. Okay? So now let's go back to the linear system. So we saw what a fixed point iteration is, and for the linear system given Ax equal to b, I want to construct a G mapping that will take an initial guess and produce a new vector out. Okay? The way that I do that is, I know that G has to be linear also. Okay? Because it's a linear problem. We're starting with a linear problem. So I'm going to write this as a matrix Tx plus C. Okay? So my G is nothing but Tx plus C. But then what is G prime? If I can do that, and I will show you a few ways of constructing your T and C pretty soon. Okay? But at this time, I'm saying that I can always do this. I can always write x equals g of xp for linear systems. You can always write this as a linear mapping of xt, the guess, to produce a new guess. Okay? So what would be g prime in this case? C is a constant. T is another constant matrix, because it is coming from a linear system. So what would be G prime? Simply T. What is G prime? G prime is derivative of G with respect to x. And it is appearing linearly with respect to x, right? So G prime in this case must be simply T, right? But now I have a problem. If I have a scalar problem, I can say the slope of the function G prime must be less than 1. Here I have a matrix. So what does that mean? When would, under what conditions would that iterative scheme converge? There is something called the spectral radius of T. That is the eigenvalues. If the largest eigenvalue of T is less than 1, then that's what they call a contraction mapping. It will always contract. It will always produce a number smaller than the right-hand side. Okay? So the condition is that the spectral radius of the matrix T must be less than 1. Eigenvalue of T must be less than 1. Okay, that's an important concept we will also see later on in stability analysis. So eigenvalue plays an important role in both the stability analysis as well as in convergence. Okay, so we have generalized it from a single nonlinear equation to a system of linear equations, as a condition that the largest eigenvalue of the matrix T, we still don't know how to construct that T, but if we can construct it, the eigenvalue of that should be less than 1. Okay? So we do the error analysis very similar. Once it is converged, R is equal to T of R plus C. So you subtract both sides from the same thing, and you get the error at P plus 1 that is T times the error at P stat. So for this map to go to 0, this mapping to go to 0, T must have an largest eigenvalue that is less than 1. Any questions? So now we are going to see how do I actually construct this matrix T. Okay, so what is the idea? The idea is make a guess for x, that means every component x1 to xn, and then devise a new method for calculating these components. So the simplest way to do that is take the first equation, pull out x1, move everything else to the right hand side from 2 all the way to n, and divide by a11. Simple rearrangement of the first equation, isolating x1 and moving everything else on the other side. But you provide a guess for all these. So they are indicated as step P. P is equal to 0 initially. Okay? So you put this on the right hand side. This is not going to equal to 0. It is equal to 0, what does it mean? I mean, it cannot be. It should be equal to x1, the guess that you have made. Then that equation is satisfied. Right? Since you're making arbitrary guess for x2 to xn, you actually make the guess for all of them, x1 to xn. Okay? And then put them on the right hand side when you calculate your new x1. Then go to the second equation, pull out x2 to the left hand side. Move everything else to the right hand side. Update your x2. Go through all of them like that, x1 to xn. Then you have the next iterate, next guess, and you can repeat this cycle. And this is called the Jacobi iteration. Do you understand the idea? Would you be able to implement it in MATLAB? Just a loop around this equation. In fact, if you take the second equation as your template, I'm just showing you the first one and the last one, but this template will work for any equation. Okay? So here, I'm going from 1 to j minus 1. These are all the elements before j, and then j plus 1 to n. These are all the elements after j. And you put a loop around this for j going from 1 to n, you have a scheme for updating your initial guess, and that is called the Jacobi. First observation, very good observation. X1p is also a guess, but I'm not using it anywhere. Yeah. Any other observations you can make on this? Can you make this scheme better? Gauss-Seidel method is better than this. You know what a Gauss-Seidel method is? These are all very intuitive methods that people come up with, right? This is, to me it looks like, if I didn't know anything about it, this is what I would try. In chemical engineering, we call this trial and error. We just make a guess, we solve for temperature, put it back, and keep iterating it. Here it has a nice fancy name, but it's essentially a trial and error approach that we have used in simple hand calculations. Right? But in Gauss-Seidel, I mean, one of the questions that you can ask is, I have now a new value for x1. Why can't I use it as soon as it is available in the second equation? Right? Why do I have to wait till I go through updating all x1 to xn before I use the new one? That's actually very nicely implementable in program, because you just need one storage location. As soon as the new one is available, you keep only one vector x, it will automatically store the new value, it will automatically use the new value. And that is called Gauss-Seidel method. Okay? So essentially you make this as p plus 1. As soon as a new value is available, you use that in subsequent equations. Okay? That's the essential idea of Gauss-Seidel method. But before we do that, let's learn how this is connected to the matrix T that we saw. Okay, for iterative method, the fixed point iteration. So this method is nothing but L times x plus v times x at p plus 1 and u times x at p. So that is A has been split not by factorization This is the equation that we have, Ax equal to B. But we are writing A as L plus D plus U. You need to probably think a little bit about that. What is L? L is not coming from factorization. It is simply the lower part of A. Pull all the lower part of A and put it into L. Diagonals of L will be 0 because D is put in, diagonals are put in the D matrix. And U matrix essentially has all the upper elements of U. So it's essentially a summation. It's not a factorization, right? And then we are saying it's only the diagonal element that gets, because that's the one that remains on the left-hand side. They all have a superscript of P plus 1. These are the lower part, these are the upper part. They are both at P. You understand that splitting of it? Once you understand that, it's very easy to construct the matrix T. Okay? So what you need to do is keep this on the left. Remember, you need to write this as x at P plus 1 equals some matrix T x at P plus B. Okay, so what do I need to do? I just need to keep this on the left hand side. So you write this as B minus U plus L at x of P, and then put a D inverse here, and that is equal to x at P plus 1. Okay, so what would T be in this case? Minus D inverse L plus U. That matrix is constructible once and for all because you know these are all coming just from A, right? And to invert a diagonal matrix is
1 over.
very easy, 1 over the diagonal elements. And you can do the multiplication, you can pass it to the eigenvalue routine, calculate the spectral radius, and see whether it is less than 1 for convergence. And you can actually, using functional analysis, people have kind of proven that it would converge as long as, this is a term that you might come across, the matrix A is diagonally dominant. What does that mean? The elements in the diagonal are much bigger than the elements on the other side. Why? You can see that if it is diagonally dominant, 1 over D would be all small numbers, right? So T essentially would be a small number then, and its spectral radius would be less than 1. Okay, so that proof has been done, I think, for. So yeah, basically what I showed you here, I'm pointing out the same thing. But Gauss-Seidel, as I said, only changes this, which translates into the concept that as soon as you have a new value in the lower part, use it. That accelerates the convergence tremendously. Okay, sometimes twice as fast as in the Jacobi method, because as soon as a new information is available, you are using it. And you can do the splitting of this in the same fashion, and you will construct a different. So the difference is this is at P plus 1. Lower part is at P plus 1 because they're all known. Okay, and the upper part is at P. And so it is L plus D inverse now. Okay, and that becomes your T. And once again, the proof for this exists that as long as the matrix D is diagonally dominant, this method will converge. It's guaranteed to converge, meaning its spectral radius will be less than 1. What can we do better than that? Have you heard of any other method? So this is just a code that illustrates Gauss-Seidel method for you to look at. I always find that when I see a code, I can understand the implementation much better. So I develop these codes and put it into the notes. In an undergraduate course, I will go through them and demonstrate and all that, but this is a graduate level course. I think if you are curious enough to learn how it works, you can go and read about it, implement it, run it, etc. So the Gauss-Seidel, built on the Gauss-Seidel is this method called the successive over-relaxation. This is the terminology you will come across in COMSOL, in Fluent, etc. So-called relaxation factor, okay, for the iterative method, okay. And what is the idea behind it? The idea is the following: you have a way of calculating an updated value for x using some formula. It could be Jacobi method, it could be Gauss-Seidel method, whatever. Okay? So using some method. But don't accept it as the actual value. Assign it as a temporary projection of the value for xj. And then relax it. The relaxation idea is given by this. And what is this? It is the actual value of xj at p plus 1 is going to be equal to the original guess that you made plus a factor times the difference between the original value and the tentative value that your algorithm projects. Okay? So Gauss-Seidel projects this value. In the Gauss-Seidel method, you will accept that and run with it. But in successive over-relaxation method, you take that and find the difference between these two. Sorry, between this and the old value. And then relax it. And the relaxation essentially says this number is called the relaxation factor. It can be greater than 1. It can be less than 1. Okay? So if it is greater than 1, it's called over-relaxation. If it is less than 1, it's called under-relaxation. Now, if you have if it is equal to 1, what happens? It is Gauss-Seidel. It is Gauss-Seidel, right? Because if it is equal to 1, this is cancels and this is t, but t is just the projected value, right? So at equal to 1, it performs as well as Gauss-Seidel, but if it is greater than 1, it can accelerate convergence. Because what you are doing is you are taking the old value and applying a difference that is enhanced, greater than 1, multiplied by a number greater than 1. So it increases the convergence rate significantly. Again, there is a theoretical analysis that says that it has to be less than 2. So if it is between 1 and 2, it's called over-relaxation method. But the proof says that if it is greater than 2, the spectral radius of that matrix T that you construct will be greater than 1. It will always blow up for linear systems. Okay, but if it is between 1 and 2, you can actually significantly accelerate the convergence rate. What does that acceleration means? The number of iterations that you need to achieve a converged result is reduced. Number of iterations is reduced. So the acceleration rate is sometimes projected like this: the error versus the iteration number. Okay, you plot this, and the slope of this is your acceleration, convergence rate. How fast does it converge with each iteration? Any questions on the idea of over-relaxation?
The bigger the pattern, then why not just use 1.9 and 1.9?
Right. There is some work that this all happened in the 60s, I think, that says the optimum value is somewhere around 1.8 for linear systems. Diagonally dominant linear systems, the optimum value is somewhere around 1.8. So you can use that for linear systems as long as you know that it is diagonally dominant. Now, the idea is also used particularly for nonlinear systems as under-relaxation between 0 and 1. If the system blows up, you try to calm it down by saying, I'm not going to use the full projected value, but use only a small fraction of the projected value. So 0.2, 0.3, etc. So this is a thing that you can play with in COMSOL. The relaxation factor is a parameter in your numerical algorithms. So if you can manipulate it, control it, bring it down to see whether you can achieve convergence. Among other tools in our trick, which would be to come up with a better guess, that will also enable you to get convergence. Any other questions? Okay, so if you go through the same mechanics of constructing your T, it gets a bit more difficult algebraically, but this is the entire equation in terms of the relaxation parameter. Okay, and then you collect all the xp plus 1 terms, xp plus 1 terms on one side and xp terms on the other side, separate them out, and you will find that the matrix T, now you have a knob. Omega is your tuning parameter. You can choose omega to be 1, 1.2, 1.7 to control the spectral radius. So the person that did this work to find out about 1.8 is optimum, essentially looked at this matrix and tried to map the spectral radius of that matrix as a function of omega to see where that optimum lies. Yeah, I say it here, somewhere around 1.7 and 1.8. Any questions on iterative methods? This is the essence of idea behind iterative methods, and we are going to see Gauss, the conjugate gradient method later on. But before that, I want to prepare us for these concepts of linear independence, orthogonality, Gram-Schmidt procedure, etc. Because we need to understand that before we understand the essential idea behind conjugate gradient method. It's also an iterative method, very powerful method for large systems of linear equations. For HPC, it's particularly very helpful because you can parallelize these very well. So we're going to switch gears and talk about these concepts of orthogonality of vectors, linear independence, etc. Okay? Any questions before we do that on the iterative methods? Okay. So if you give me two vectors x1 and x2 and I say that they are orthogonal, what does it mean? The general notion of orthogonality is that they are perpendicular to each other, meaning that the angle between them is 90 degrees. Okay? So the definition of the inner product of two vectors, x1, x2, you can do it in vectorial form or in a geometrical form. The inner product is essentially summation of all the components from vector 1 and vector 2. If this vector has n numbers, this vector has n numbers, the inner product is given with the dot symbol between, and it is essentially take the product and sum them up. MATLAB does it automatically for you. You have two vectors, and you do the matrix multiplication with a row vector and a column vector. This is a row vector and a column vector. It will give you the same product. Now, geometrically, it is a magnitude of x1, magnitude of x2 times the cosine of the angle between those two. Now, if the angle is 90, cos of 90 is 0, and that means that these two vectors are orthogonal. Okay? So the requirement for orthogonality is that the inner product of these two vectors must be 0. For example, if I1 is a unit vector with components 1 and 0, I2 is a unit vector with the component 0 and 1. Okay? So this is 1 but 0 in the other direction. This is 0 in the first direction but 1 in the other direction. And if I take the inner product, it means 1 times 0 plus 0 times 1, that is 0. So unit vectors are orthogonal in that sense. But you could have any two vectors, if they meet that condition of the inner product being 0, that says that they are orthogonal. If they are orthogonal, that means that they are linearly independent. Do you know what the concept of linear independence is, right? What does it mean? How would you express it in English? If I give you 10 vectors, what does it mean to say that they are linearly independent?
So no combination of other 9 will...
Exactly. You cannot produce any one of those vectors as a linear combination of the other 9. You cannot take the other 9 vectors, add them up with any weighting factors that you choose, add them up to produce that vector. That means all of them are independent. No one is expressible as a combination of the others. And the way to express that condition is given by this equation. Okay? So if you give me n vectors, x1 to xn, I multiply each one of them by a factor alpha 1, alpha 2. These are scalar numbers. And if that is equal to 0, the only way that is possible is each one of alpha 1, alpha 2, alpha n is equal to 0. Because they are linearly independent. I cannot express any one of them as a linear combination of the others. Okay? And the way to test for linear independence is, remember, each one is a vector. So I can write it as a column in a matrix and assemble all these vectors. And when I do that, if I write A times alpha, alpha is a vector consisting of these coefficients alpha 1 to alpha n. So that will essentially be x11 alpha 1, x12 alpha 2, x13 alpha 2, hash all that. And do the same thing for the second one, etc. And you will find that this is equal to 0. That means, what can you say from that condition about linear independence? When would those vectors be linearly independent? If A is invertible, non-singular, right? If A is singular, that satisfies the 0 part. Alpha can be anything. I can satisfy that, right? So A must be not 0. Determinant of A is not 0. And that's an important concept. This concept of linear independence, we will later on extend to functions. So if you give me 10 vectors, when are they linearly independent? If you give me 10 functions, when are they linearly independent? The same idea. If you cannot express any one function as a combination of others, they are linearly independent. Why are these linearly independent sets important? Because I can then construct any other vector using these vectors as basis, as reference. Okay? So I can construct a reference frame using these independent vectors, and any other vector can be represented as a linear combination of these in that subspace. Same idea applies when solving differential equations to functions. Because what are functions as solutions to differential equations? Some arbitrary function that must satisfy a differential equation. If I can express them as a linear combination of a set of basis functions, then I can try to construct a solution. Okay? And we will extend those notions later on, but for now, let's just look at the next thing to look at is the orthogonalization process. What does that mean? And this is important to understand the conjugate gradient method and other iterative methods that are based on that, so-called GMRES, which is used in COMSOL, generalized minimum residual iterative methods. We already saw what residual minimization is. So what is the Gram-Schmidt idea? Have you seen that? You have not seen that. Okay. So let's focus on the algorithm is there, the code that I've given, and MATLAB has a code to do that. But I want to focus on capturing the essential idea of what the Gram-Schmidt process is, because the idea from here will be applicable in situations with eigenvalues and eigenvectors later on. So if you give me a set of linearly independent vectors x, but they are not perpendicular to each other, graphically I can represent only with two vectors at best. So this is a vector x1, this is vector x2. They are linearly independent, but they are not orthogonal. So if you give me a linearly independent set of vectors, I can test them. If you give me a set of vectors, first thing I do is I test whether they are linearly independent. How? Put them in that matrix form, check the determinant. If the determinant is 0, I immediately tell you that they are linearly dependent. Right? If they are independent, like in this case, then I need to construct a basis that is orthonormal, perpendicular to each other from this set of vectors. When would two vectors be linearly dependent? Geometrically, can you think of a situation? This is x1 and that is x2. They're both parallel, right? So you just multiply it and shift it, you express one and in the form of the other. So the moment they are not parallel in two-dimensional case, you know already that it is linearly independent. So the essential idea is take your first vector x1 and normalize it and call it u1, meaning its dimension, its vector length should be equal to 1. Okay? Once you normalize it, that would be your first vector. Then you want to find a vector that is perpendicular to u1. So you're going to construct a set of vectors u1 to un. They're all perpendicular to each other, and their unit length is, their length is all unity, 1. That's an orthonormal basis, right? So this is the first step. We just normalize it. Take x1, divide it by the norm, you normalize it. The next step is what you need to understand. What am I saying here? I'm saying I'm going to construct a new vector u2 prime, which is x2 minus a factor multiplied by u1. That is, I'm going to take a portion of vector along the x1 direction, u1. So u1 is in the same direction as x1, right? But I need to take enough of that so that when I subtract it, what I'm left with is perpendicular to that. You understand? So if I take, for example, this length and then I subtract it, vector subtraction, right? So this is your x2, and if I take u2 and subtract it, the remainder will be like that. That's not going to be perpendicular. So I adjust the length until it becomes perpendicular. So that length is what is determined by this C0. I know already u1. u1 direction is known. u1 length is known. It's 1, right? So I want to find the length of C0 such that this difference vector which is pointing in the U2 direction, is perpendicular. Is that clear? Graphically, you follow
It
what
can be
I'm
more
saying?
than one, right?
Huh?
It can be more than
It can be more than one, it can be less than one, because I don't know what is the length of x2. I haven't normalized it, right? And so this idea of a subtraction, you should imagine geometrically only for 2D case, but other cases, algebraically you can extend it, geometrically you cannot show that. Right? So I have another vector, and I'm going to adjust its length such that I subtract enough in the x1 direction, and that is C0 times U1. That is what is enough. I'm subtracting that, so what I'm left with is in the direction perpendicular to U1. So another way of looking at this is I'm subtracting some arbitrary component to form a new vector U2. Now I can assign a property and ask the question, when will U2 prime be perpendicular to U1? When the dot product between U2 prime and U1 is 0, right? But can I impose that condition arbitrarily? U1, U2 prime dot is equal to 0. I can, because I have 1 degree of freedom. What is the degree of freedom? C0. I don't know what C0 is. So I can solve for C0 by imposing that condition. U1 transpose dot U2 prime, the inner product of that should be equal to 0. That means I apply this to the right hand side too. I'm applying this to the left hand side of this equation that you see here. That is, I take that equation and multiply both sides by U1 transpose, term by term. Right? So when I do this, I'm going to get a number that won't be 0. Right? And U1 prime dot x2, and x2 is given, minus C0 times U1 transpose U1. What is that? Just 1, because it is unit vector, right? So I know this, I have just calculated this from here, and this is given, okay? And so I can calculate what C0 is by requiring that this should be equal to 0.
Is there always 0?
Which one?
The transpose of U1
And
yeah.
U2? No, they won't be 0. In general, they won't be 0. That's what I was trying to illustrate by the graph here, right? What is x2 minus C0 U1? x2 is this vector,
Yeah.
right? And then I'm taking a vector in the U1 direction, some unknown length. So if the length is this, then the subtracted one will be something like this, right? This minus this is this vector. That vector is not perpendicular to x1, but I can stretch it. By changing the value of C0, I can stretch it until I subtract enough of it so that this becomes.
So that is the U prime too, right? The one that you are showing in your pen.
Yeah, that is U2 prime.
So U2 prime is always perpendicular to U1.
Yes.
That's what I was asking.
Yeah, I want to make it perpendicular. Okay. That is the Gram-Schmidt procedure. The Gram-Schmidt procedure is, if you give me x1, x2, x3, x4, I need to construct u1, u2, u3, u4 from the x's such a way that they are all perpendicular to each other. So I want u1 to be perpendicular to u2 prime.
C0 gives that to us.
C0 gives me what length should I subtract in the u1 direction to get that. And once you understand this, you have an algorithm to calculate C0. Okay? And you can then normalize your u2 prime. Okay? And next step is, I cannot draw it, you can only imagine the same logic. You take x3, the next vector, you know x3 is linearly independent from x1 and x2, or u1 and u2. So take that and subtract a component in the x1 direction, subtract a component in the x2 direction, so that you're left with a vector u3, which is perpendicular to u1 and u2. Now c1 and c2 are both unknowns. There are two unknowns now, right? So how would you determine that? You would impose two conditions. The two conditions are u3 must be perpendicular to u1 and u3 must be perpendicular to u2. Right? So you take that equation, take the dot product with u1, you get this, take the dot product with u2, you get this. That gives you c1 and c2. Okay, so the unknowns in the sequence are just these coefficients, c1, c2, c3, etc., and that are determined to construct this series of vectors, U3 prime. Any questions on that? Once you figure this out, these are all by induction. You follow the logic and then you say, okay, I can now write down the general procedure and put it into a MATLAB code. So essentially, starting with normalizing the first vector and starting with the second vector, simply subtracting one by one all the components. So it goes from 1 to s minus 1. So in the second one, there will be only one component. Third one, you will subtract two components. Fourth one, you will subtract three components, etc. And then normalize it. And each time. So it will return a vector u1, u2, un that will be orthonormal to each other. And there is a function called orth in MATLAB that does this. You pass it a set of vectors assembled in a matrix. It interprets each column as a vector. And then the output that it produces will be another matrix containing u1, u2, un as columns. And they would be orthogonal to each other. Okay, any questions? Okay, the eigenvalue problem. You're all familiar with the eigenvalue problem, right? So maybe we can go over it very quickly. So the eigenvalue problem essentially is one where given a matrix, an operator, if you multiply it by any vector, it's going to produce another vector. That's what happens, ax equal to b. Okay. Here the problem is, give me a and b, I need to find that vector, which when I multiply, it gives me b. Right? So a is treated as a machine that converts vectors to other vectors. Okay? So it's a transformation, it's a process. But eigenvectors are those that give you back the same vector. If you multiply it by x, it gives you back the same vector, except it is stretched. And the extent of stretching or contraction is your eigenvalue. Okay? And there is a way to find that particular vector and the eigenvalues by simply rearranging this as a minus lambda I multiplied by x equal to 0. And it is a homogeneous equation. And you can treat this as another matrix. So a matrix times a vector equal to 0 will give you non-trivial solutions for x only when the determinant of that is equal to 0. You get the same idea. Right? So you set the determinant of this equal to 0. And the freedom that we have, the unknowns that we have are all these eigenvalues lambda and the corresponding eigenvectors x. So if you have an n by n system, that will give you a polynomial of degree n, and you can find out, in fact, in your first assignment you did this, there is a poly function that calculates the characteristic polynomial and all the roots. There is also an EIG function. All these work well as long as you have 10 by 10, 20 by 20, 100 by 100 system. But if you have 100,000 by 100,000, all these methods would fail. So once again, we are talking about what are the needs for calculating eigenvalues. If I have a 100,000 by 100,000 equation, I don't need all the eigenvalues, but I need those eigenvalues that are on the margin, because the stability is determined when they go from negative to positive, for example. So I need to develop algorithms, and MATLAB has these algorithms we have used to find select eigenvalues in a certain neighborhood of eigenvalue space that you specify. So you're going to build towards developing those algorithms. But this is essentially the eigenvalue problem, solving for lambda and then solving for the vectors, and the EIG does that for you. I think I have a few examples here that you can look at because you have already played with these. And this is the characteristic polynomial. I guess we are almost out of time, so maybe we will stop here. How am I doing? 25 pages. I still have one more lecture to cover this. And then we'll move into differential equations, discretization of that, and solve those. So we'll stop here for today. Any questions? Okay, so we'll see you on Monday. Or before that, if you have any questions regarding your project, please feel free to drop by, because you want to start defining your problem. What are the equations? What are the boundary conditions? What is the geometry, etc. So if you have any questions on those, just drop me an email and drop by.